Okay, let's go ahead and get started on the next one. So the next one we have today is the bridge plan set reading presentation. My name is James Corney. I am with the Structures Group up in Central. I'm the structures construction engineer. I've been there for last 7 years. It's been a good time. Before that, I was in Las Vegas, Nevada, where I was a design engineer. Designed some pretty long bridges, 1,000-foot long bridge for the airport. And if you've ever been to Las Vegas and rode that tram that connects Bellagio down to the Park MGM, I did the analysis for that structure, won an award for the concrete elements on that structure. Engineering is fun, but I am an engineer because what we do is build stuff, right? So when I was like 8, I was like, I want to be an architect, but they just draw pretty pictures. What we do is make stuff really cool. So my name is James Corney. Put my name here. That is my email address, jcorney@utah.gov. We're all here to help, right? So if you guys have questions, ask them today, or if you got something that you find out later, please shoot an email, talk to your mentors, go up the chain, find someone like me. So yeah, let's start with some hands. So how many of you have inspected new bridge construction? Great. So it looks like maybe half to two-thirds of you. That's excellent. This will be a lot of review for those that have. For those that haven't, hopefully this will really help get some foundational elements going for you. Okay. So let's start by talking about the outline. I'm going to start with an introduction to bridge, how important it is, do a quick review, move into some rebar basics, and then dive into those plans, organization, and then sort of an easy, medium, hard on bar reading, and then just follow up a little bit of extra stuff at the end. So, as a warning, this presentation was originally written by someone in the structures division. So there's some writer's bias here. That being said, everyone already knows that bridges are cool. So in terms of square foot area, bridges may be small compared to paving, but great things come in small packages. And pavement is placed on dirt, and that's easy. But bridges, they're placed in the sky, and that's really hard. And they're designed to support a 100,000-pound truck in each lane on an 8.5-inch thick piece of reinforced concrete, and that's the deck. Let's think about that for a moment, okay? The bridge deck is 8.5 inches thick, but a typical pavement is 10 inches of concrete on 3 inches of asphalt, on 4 inches of untreated base course, on 6 inches of granular borrow, on a geotactile over natural grade. There is a big difference between placing stuff in the sky and then, putting stuff on the ground that makes a smooth driving experience for our trucks. And what is that difference? It's the reinforcing. And yes, all those circles are pointing out reinforcing callouts. It may seem a little bit overwhelming right now, but we will get into that. It's not nearly as confusing as it seems. So remember, structures are the best and most complex and expensive pieces of UDOT's infrastructure, and they are much cooler than pavement. But just to drive home how important what you do is, I want to make it clear, bridges must not fall down. That makes inspection of these elements very important, and that's pretty obvious, right? And the truth is, to get to the point that bridges would be in trouble, we'd have to have a lot of problems. So I'm not suggesting that we're in that kind of a danger zone. Instead, what we're thinking more about is maintaining good quality structures that we don't need to repair. And that's where the gut check of bars looking like they're in the right place smashes up against bars actually being where the plans say that they should be. And contractors do this all the time, and they will say so, but the plans are where the engineers spend months making sure that bars are where they need to be for strength and durability. Okay, so that's my pitch on the importance of bridges. So now let's move on to an actual information dump. I've titled this slide Quick Overview because it's not about rebar, but there is actually a ton of information here. I'm going to go quickly So if you have any questions after the presentation, please reach out and ask, either to a mentor, to the project team, or to the structures division, me. Now, I think it's a good idea to know the basic names of bridge structures and what they are. This hopefully is already familiar to you, but it's important review to know terms that when the contractor or engineer says, doing such and such will impact the diaphragms, you'll know what that references. So first, substructure and superstructure. These are separate terms because they are separate. The substructure supports the superstructure. Let's start with the substructure. What is in that? Well, we've got foundations, columns, bent caps, abutments, and within each of these categories, we have different types. For example, we have shallow and deep foundations. So, quick question, can anyone here tell me what the most common type of foundation in Utah is, whether it's shallow or it's deep? Anyone willing to? So is that shallow or deep? That's right, deep. So driven pile, we drive those things, 50, 120 feet into the ground. They're very deep. And the benefit of that is it prevents that bridge from settling, even though the soils might not be that good. Okay. So like the picture here, where you see round driven piles in the top left, that's it. That's our number one type of foundation. For bent caps, we have integral caps and draw caps. Integrals are caps that are integrated with the superstructure, like this. And they are pretty rare because they're complex and expensive compared to the typical situation where the bent cap is below the girders. For abutments, we have integral, semi-integral, and seat-type abutments. In Utah, we primarily use integral abutments, like you see in the photo. What makes integral abutments interesting is that they lock the girders into a concrete block or diaphragm, and they don't cost as much as integral bent caps, but they're still a little more pricey than non-integral abutments. But all that concrete prevents water from passing through the joints and causing corrosion underneath the superstructure. It's an engineering decision that costs more, but provides better long-term durability. Notice that durability is the key, and that's a long-term view. Price is important, but that durability, that long-term performance is often worth the cost. Now, you might have noticed the little gap under columns. For the most part, columns are round, nothing too shocking there, but there are some things on a column that are important to know about and pay special attention to, and that's connections and plastic hinging regions. In an earthquake, the columns bend and flex. It might seem a bit crazy that a 4-foot diameter block of concrete can bend, but it can. And we really need to double check the connections to make sure that they're installed the way they were designed. And the connection extends beyond where the column physically connects to the footing or the cap into what's called the plastic hinging region. This is basically the 3.5 feet above the connected foundation or below the cap, because a lot of bending happens in those areas. The concrete in a big earthquake is actually expected to break in a controlled way in those plastic hinging regions, kind of like the crumple zone of a car. This video here is what's called a shake table, where researchers actually simulate full-scale earthquakes. The critical zones are the connections, particularly at the bottom in this case. And the plastic hinge region is at the bottom of the column, which is bending all over the place. It's serious stuff. So that's the substructure. Now the superstructure. The superstructure is made of girders, diaphragms, decks, parapets, expansion joints, and contraction joints, or construction joints. Just like with substructures, there's multiple types of everything. Girders are typically steel or precast concrete. There are actually many other types of girders, from box girders to trusses, and materials from plastic to wood. But 99.9% of Utah bridges are steel or precast concrete. So if you see something else on a job, it might be a good idea to reach out and learn what makes that different. Precast girders tend to be a little less expensive for our typical straight overpasses, so we do tend to use those most often. Diaphragms tend to be steel, but there are some concrete varieties. In the picture, you see big steel diaphragms because steel bridges require big diaphragms, unlike the concrete bridges, which tend to require something less. Decks either have partial deck panels, like you see at the top photo, which are precast concrete pieces which span between the girders, or are full depth cast in place where wooden formwork is required to support the full thickness of the deck. We're sliding a bit more toward using precast panels rather than full depth deck these days, because they occupy half of that deck with precast concrete, which can make the construction of concrete placement activity shorter. That being said, they have their own drawbacks and inspection issues that I'm not going to talk about today. Expansion joints usually come in compression joints or strip seals. The difference is that strip seals are more expensive and require embedded steel rails. So we only use those when bridges move enough to require them. Construction joints do not move and are listed here just to call out that they're different from expansion joints. Those construction joints are just there because of a pause in construction, and reinforcing passes through that joint. As a side note on construction joints, they are a necessary evil. Sometimes we just need them, but they're weak points in the final product and can often lead to durability issues. And finally, let's talk about a couple of important words that, again, you probably already know. The first is longitudinal. It is along, get it, the direction of the girders and the traffic. Usually this is the same direction. To make it more clear, sometimes people will say bridge longitudinal, essentially along the bridge. Then there's transverse, which is the opposite, directly across the longitudinal. Skew, it's how the abutment lines up with the girders and the traffic. As you can see in the picture, the girders are skewed to the abutment. If there was no skew, the transverse picture would line up straight down that abutment line. And finally, we have placement sequence. Some bridges are too long for the contractor to place in one activity, or there are design requirements which require the deck to be placed in a certain sequence. This picture shows a part of the deck placed and curing, while the deck area next to it is just exposed reinforcing steel, waiting for the next part of the placement sequence. Here's where the construction joints pop up again, like you can see in the bottom right of that picture. But it's not always huge bridges that require placement sequences. Sometimes a small bridge will require a sequence for a special condition or even at the contractor's option. If concrete supply is constrained or work windows are short, you might end up with a construction.
Does everybody know what it means, like placement sequences? So they don't. This is the say, hey, what exciting with me, right, guys?
Yeah, this is actually where my quick refresher is done. So, I went over a lot of things. If there's anyone that has a question right now about just some basic bridge stuff, this would be a great time to pause and get some questions answered before we move on to the next topic. So let's move on to rebar basics. So can anyone here tell me why structural concrete needs reinforcing steel? Anybody? There we go. That's exactly what I was going to say next. Yeah, concrete is garbage in tension, right? It's made for compression. Once it cracks, it's done. Good job. Yeah. So we need steel to provide that tension capacity, and we call it a composite system. Different materials working together to make something better than the individual parts. So if the reinforcing steel is not there or in the wrong place, we have a problem. See it again. Yeah, it's bad.
I know Lonnie would have talked about energetic compression a little bit, right? In this stage. But then, I know the academy, certain academy guys, so I apologize. You guys understand me doing compression, right? If you don't, it's what you mean.
Yeah. So it's a composite system where that reinforcing steel, it's kind of great in everything, but steel's expensive, right? So you mix it with the concrete can take all that compression load, but if you're going to pull on it, you need something. And when you have bending, like a beam crossing over a road, when you put that load right on top, the center of that beam, the top goes into compression, the deck goes into compression, but the bottom of that girder is in tension. And then if it cracks, it's done. So you need that steel. So next up, let's talk about bar sizes. You all know that bars come in different sizes, but something you might not be as familiar with is exactly how the actual size is related to the name or the bar number. The bar number is just how many eighths of an inch that bar diameter is. So a number 4 bar is 4/8 or a half inch in diameter. A number 8 bar is 8/8 or 1 inch. An 18 bar is 18/8 or 2 1/4 inches. That's a big bar. You're probably not going to see one of those, but they're there, right? It might be easier then to tell the difference between a number 4 and a number 8 bar, but there is a way to be sure, and that's with bar identification marks. There's another way to be sure, and that's with measuring tape, because that's how it works, right? That 1/8 inch that's the bar mark. So if you take a tape and you drop it on that bar, but that's a quick check. You can always tell because every bar will be marked, as long as I guess it's not like a 2-foot piece or something like that missed the mark. But every bar will be marked. And if I zoom into this picture, we can see a bar mark from one of our UDOT jobs. The NU at the top is the producing mill. In this case, it's Nucor. The next number down is a 6, meaning this is a number 6 bar. Below that, we have an S, which means that it's made of A615 steel. Note that if there was a W here instead of an S, or if it was an S/W, that would indicate that it's a weldable A706 steel bar, which is simply better than an A615 bar. And that can be used interchangeably with that, except in columns. Columns are critical elements, so they must use the better W-marked A706 steel. Then at the bottom, there's a 6 and a 0, which makes a 60. So it's a 60 KSI or 6,000 pound per square inch steel. That's UDOT standard. And finally, we have coatings. Bridges only use coated bars, but they can be green epoxy coated, or they can be the shiny galvanized coated. This protects the bars from rust, and rust or corrosion is a big driver of why we do what we do. Okay, so now let's move on to plan organization. It's probably a good time to stop and say, does anyone have questions about rebar before we move on to plan organization? Do we still get metric bar? Well, that's fun. So what you see here, bar marks, 4, 5, 6, 7, 8, 9, 10, 14, 18, those are American numbers. Most of your bars should be, US sizes, but there are metric sizes. They're equivalent to US sizes, but there's a bit of a chart that you'd probably need to reference to check that. We don't have a standard UDOT manual that shows that, but there's a lot of CSRI guides that are free available for that, or just straight up Google, right? Google's the best way to find super standard information like that. Thank you. I didn't actually realize that we were still getting a bunch of metric bar. That's sad. Really, thank you. Any other rebar questions? No? Okay, so let's move on to plan organization. First thing to know is that all bridge plans go through a structures division organization and review process. That means that every plan set will have a similar organization and style. Now, not everything is going to be the same from project to project since different engineers get involved. But in general, if you understand one plan set, you will be able to understand another. particularly when you're dealing with UDOT work. I also want to mention that this is specifically talking about bridge and stop talking about structures stuff. But anytime you have reinforcing standard drawings, whatever, this stuff is pretty much applicable. It's going to give you that good foundation for how to read barrier drawings if you were ever inspecting something at a facility, something like that. But we're focused on bridge, where we are very specific on how we do things. So this is really good for structures, okay? So every UDOT structure plan set will start with a front page, which we call the situation and layout. It's actually the title of the sheet. That means that on this sheet, you will find basic information for how the bridge is situated and its general layout. You'll find the location plan here, along with information about the routes on and below the bridge, and a whole bunch of general notes and information. You'll also find the plan view, which is an overhead view of the bridge, and elevation view, which is basically looking at the bridge from the side. The profile lines and typical sections will also be shown and are sometimes it's required that that information crosses onto a second page, which is why those bits of information aren't on the screen right now. But that's probably not as important for what you do every day. Anyway, now that we're talking about the actual plan set, I want to make a really important point about plans. Really hard to understand a layered and complex structure from a single detail. So in a plan set, the same thing is almost always shown in multiple views. The situation and layout is a really general page showing the whole bridge, so there isn't enough detail to construct it. But in order to help you understand the situation and layout of the bridge, it's shown from the top and from the side. In fact, considering the location plan, this also shows how plans drill down to provide more detail. The location plan shows the bridge and where it is. The plan view essentially zooms in to show better detail on the size of the bridge and the lanes. Zooming in again on different pages, we can see how the girders are placed, and in this case, where the partial deck panels are. Zooming in again, we can see the reinforcing placement. I'll talk about that in more detail later. And zooming in again, another view is provided to look at the reinforcing from the side, in this case, longitudinally, providing more information. All these different views may seem like information overload, but it's all different pieces of the same bridge. And what I'm really trying to say is that if you don't know where something goes, there may be a better detail of it somewhere else. To inspect a bridge, you will need the whole plan set. But to inspect a bridge deck, you might just need to take 2 or 3 sheets to the deck and leave the rest in the truck for reference. The index on the front sheet can help you find what you need. All this information is helpful, and once you get used to plan reading, it does make a lot of sense. So, pop quiz. Looking at this index of sheets, can someone tell me what kind of foundation this bridge uses? It's not a trick question. I'm just pointing out how sheet names are supposed to be clear and helpful. Driven pile, that's right. And like we said before, driven pile are deep foundations. The names of our sheets are supposed to be very descriptive of what's on them, right? Driven pile sheet, bridge deck sheet, right? And the next thing to talk about is the reinforcing steel schedule. Every structures plan set has these pages at the end. These sheets include a list of every bar on the bridge, sorted by location. It gives each bar a name or bar mark, it indicates its location, and then describes the bar, including its shape. This is shown through bending diagrams, which are included on each of the reinforcing steel sheets. So each bar has a type which connects it to the bending diagrams and list of dimensions. So here's the next question. Is someone willing to describe that A1 bar to me? I haven't gone into it yet, so this is based on experience. Can anyone describe that? Reading the schedule, what would you expect to see in the field as an A1 bar? It would look like your type 1. That's right. It's going to be an L-shaped bar, and the shorter leg is going to be 3 foot 4 inches. I think that's clear enough. Yeah, 3 foot 4 inches, and the long leg is 12 foot 9. So going down the list, we see that the A4 bar is not type 1. It's type 18, which is a stirrup, having a 135-degree hooked end on one side and a 90-degree hooked end on the other. And the A5 bar is a type STR, which just means it's straight. Now, why do the engineers go through all of this trouble to describe each of these bars? Because this is for the fabricators. It's a purchase list. Every bar that is going to be purchased for the structure. Now, you can and should use it to make sure that we got the bars we paid for. This schedule shows the total quantities of bar, and more importantly, lumps everything together by bar mark. So these bars are bundled, tagged, and delivered to the site. Please take the time to know which bundles are going to be used and where. If you're at the abutment, you'll want all the A bars used. We have had situations where concrete placement began before someone noticed that literally half of the bar bundles were still hanging out in the staging yard. They had to bring in a crew from California to redesign the entire, in this case, buried bridge culvert structure. And they had to do a lot of work. It happens, right? So just be aware. It's a great check to know that the designer said we need 376 bars. The fabricator tagged and provided those bars. Okay, now let's get into specifics. Unless anyone has any questions about where we are so far. Yeah, that's a great point. So when it comes to bars, the bars provide that tension capacity, right? So if you get them super dirty by something like mud, it really interrupts the ability for the concrete to grab onto that bar like it's supposed to. So keeping a bar clean, very important. Another fun thing is that you take it and you just grab one bar and you just walk it onto the bridge deck, it can get torn up, right? That epoxy coating is not super strong. So broken coating is bad. Absolutely, that's right. So you get that damaged bar, it just, you have this shield on the bar, they broke the shield, it can get totally corrupted, contaminated. So there are means to fix that. Typically what you're gonna see is a special spray solution where they just spray that bar. When they do that, now we're kind of off topic, but when they do that, please try to get them to put a backing plate or a piece of cardboard behind that bar when they spray, because they just go for it. And what you end up getting is a smooth plastic on the concrete below the bar. Well, smooth plastic and concrete bonds don't go very well together. So, that's just a nice thing to be aware of. Great comment. Thank you. Any other? I believe it's in the spec, but if nothing else, it should actually be on the can that they have. So take a look at it. Different products might say different things. Usually it's pretty quick though. That spray, it's like a fast setting spray paint. It does solidify pretty quickly. So usually it's not a big concern. It takes quite a bit of time to get the placement going. So it should be fine, but it's a really good question and it's a good thing to check on the can. Great conversation. Thank you very much. Okay, let's get into specifics. The column is vitally important, but it's also pretty easy from a rebar plan reading standpoint. This is a detail from bent 2 column details sheet, but that in itself was already a bit confusing, right? What is a bent and why is it number 2? Well, at UDOT, we number each of our supports. So this bridge starts with abutment 1, goes to bent 2, and ends at abutment 3. Once you know that, it's actually pretty easy to figure out where you are based on the number. But what's a bent? Well, we call them bents, but other DOTs call them piers. We just needed to pick a name so that we'd be consistent. Originally, bents were called bents because they're rigid connections that literally bend around. It's not straight, it's bent. Pretty simple. So let's get back to the plan and start looking at rebar. First thing I want you to notice that the only rebar in the column, only the stuff in the column is drawn in black. There's definitely bars in the footing, and there are bars in the cap, but the footing bars aren't shown, and the cap bars are light gray. That's because on this sheet, we're focused on the column. If you want to see the footing, there's a different page for that. Having lots of pages, again, sounds like a hassle, but it's actually the only way to make this complex detailing clear. So the first thing to do is look at the big picture and then zoom in. We have the footing, column, and cap shown here. We also see that the total height of the column is 19 feet, 3 inches, and that's for both columns. That's the general feel for what we're trying to have built. But looking at this detail on the right, we can tell if the column is, can we tell if that column is even round? Because no, we can't. That's why we need more details. And those detail locations are called out with section cuts. In the column, we have a section cut for section AA. Now I want to pause here for a second, right? And as a side note, before I remove this picture, I want to mention that here you can see that all our straight bars are epoxy green and the spiral is galvanized. This is totally fine. And it's pretty common to mix and match like this, particularly in columns, because those spirals are really hard to epoxy coat. But you may have noticed that the bars coming out of the piles are not coated at all. That is, and that's actually even a bit of rust on them, right? That's pretty much the only bar that UDOT doesn't require to be coated in a bridge. And it's because they're so deeply embedded into the concrete that we feel that they don't need to be coated. It's kind of weird. That's how it is. Everything else, though, should be coated. Anyway, let's talk about this section. Section AA gives us that detail we were missing from just looking at the side view. But there are some fun things about the section cuts for you to know. The detail, section AA, represents the exact location where the section cut arrows are shown. In this case, you can see right above that cut, there's some bars in the middle of the column. But since that cut happened below those bars, they're not shown in the detail. The direction of the arrow also matters. In this case, the section is looking down. A lot of times, it doesn't really matter. But if the section isn't round, say if we were looking at a parapet, knowing what direction the cut is looking in is very important to set a traffic sight base. So with that, let's look more closely at the section detail. With this, we now know that it's a round column. It's also 3.5 feet wide. We also have a better look at the reinforcing. Looking at that section, we see a round bar. And we can see that bar has a label, 6C5, 6C6. Each of those marks is a bar included in the reinforcing steel schedule. So why do we have 2? It's because this detail represents 2 columns. You can see we really need to use the details together because there's information we need in each of the details. The section cut always comes from somewhere. It really is like zooming in. So you can't think of a detail as a standalone piece of information. You zoom in to see that extra detail, but you need to zoom out to see where it all fits in. So zooming out, we see that round rebar is actually not a closed ring. It's a bunch of zigzags. So each loop around drops, creating a spiral. The snow in this picture is kind of nice because it makes it easier to see the way that spiral spirals down. Anyway, The point is that the drawing does its best to show you what's going on, but ultimately it's still just a sketch. So knowing that the zigzag means spiral is something that you might need to experience before it totally feels obvious. Let's go back to that bar mark. 6C5, 6C6. Just this label alone tells us something important. The 6 at the beginning lets us know that it's a number 6 bar. The C5 would be the reference to that bar schedule that we looked at earlier, where we see that there's only one of each of these 465-foot long or 465-foot 9-inch long spiraled pieces of steel. We can also see in the detail that this spiral bar is set 2.5 inches clear from the surface of the concrete. This is what we call concrete cover, and it's very important for protecting the reinforcing from water that can cause rusting. Because, surprise, rusting causes damage, and damage to columns can be bad in the next earthquake. In this picture, we can basically see where each of the vertical bars is because the rusting has caused a crack right over. Clear cover is a game that engineers have to play. The larger the cover, the better the protection, but the weaker the structure. Because concrete by itself is garbage in tension. And rebar in the wrong place doesn't help. So making sure that the clear provided matches the plans is very important. That being said, and this is not a trick question, can someone tell me how you check clear cover in the field? Just measure it, right? Once your form's up, it's just put a tape on it, right? There are all kinds of fancy things. You have your column cage will often have little offset wheels on it to make sure that what they construct is, simply to the right size. But a lot of times we like to think that, because we're building something so big, there has to be something special, some specialty tool. But really, you have that tape measure, just measure it, right? It's good. The basics are the same, whether you're building a bridge or building a patio. Measure twice and cut once, all that stuff. And you guys are literally the second measurement of that statement. So the last thing to mention here is that the TYP in the column or in the callout is short for typical, meaning that this measurement applies to everywhere in this detail where it looks like it should. So it's shown on the left, but it's the same bar in the same section. So it applies to the bottom, applies to the right, applies to the top. Next up, we have the vertical bars, or we might say column longitudinal. Because the section cut is cutting through those bars, you can see that they're drawn like dots, like a section through the bar itself. Looking back to the side view, you can see the dots there look kind of stupid. Big dots, little lines. That's showing that the spiral bar we talked about before is going, in and out of the page. The dot itself is not supposed to match the actual size of the bar, just like the line does not match the actual size of the bar. It's just a symbol that's supposed to mean something to us. Anyway, looking back at the 1611C1 and 1611C2 bars. Here, we see that the way it's labeled is a little different from how that spiral was labeled. What we have here is a 16 in front. That just means there are 16 bars here. You can count them, but the drawings themselves are considered sketches. It's really the callouts that matter. So we have 1611C1 bars. What's the bar size for this one? Does anyone want to tell me that? 11. Very good. And that means that they're 11/8 of an inch or 1 3/8 inch diameter bars. They're also EQ-SPA or equally spaced around the column, looking something like this. You might be wondering what those bars in the middle are. Those are stabilization bars to keep that noodly cage from flopping all over the place. They're not shown in the plans, but in general, it's okay to have extra bars used to keep the actual structural bars in position. It's a good idea, right? To take that visual look, make sure that they do feel right. It's also good to take that tape and measure once in a while. Try not to get overly focused on being like an 1/8 of an inch spot on, because it's the real world. It just isn't going to be that tight. We do have some tolerances, but you do want to approximately be to the point that you're like, I mean, could a bird fly through that one? Like that's not great. Right. So equally spaced, it should, it should look equally spaced. Okay. Let's touch on that plastic hinging zone again. This is the area about 3.5 feet above the footing. It's an earthquake issue because this is where the column bends. It's designed to break off the concrete cover in this area, which exposes the reinforcing steel. This comes back to the idea that more cover is not better, just like less cover is not better. This picture is from a job where UDOT Structures was called out to site because the contractor didn't follow the plan and put a disconnected spiral in the plastic hinging zone. In an earthquake, when the concrete cover pops off, that means that the spiral would be free to unwrap and the column could fail. In response to this finding, the contractor here disassembled the footing bars, pulled out and retied the columns because of this mistake. It is not fun to redo work, but huge kudos to our inspection team who found this issue and kept that bridge safe. One thing to mention here is that the sooner you find issues, the more likely the contractor will fix them and meet the contract plans. Money makes the world go round. Construction is a business, and contractors don't have an infinite bank account. So if the concrete in that footing was placed, I can virtually guarantee that the contractor would not have agreed to break that column cage out of the foundation and refabricate it, if that was even possible. So that was columns. And I called them easy because we really only have to worry about 2 bars, the vertical one and the spiral. But even with that, there's a lot to know about overall dimensions, section cuts, clear cover, bar marks. So it might have seemed like a lot. So moving on to pile caps, unless anyone has a question on what we just learned. So in all of our examples, that's right, it was on the bottom. But when you have a big multi-column beam that has a big, deep bed cap going on the top, it actually happens bottom and top. So in that seismic shake table design, it was just a singular column, so it was just at the bottom. So please pay attention to the plans. It should let you know where those are. Okay, so let's move on to pile caps. The pile cap is more of a medium instead of an easy, but now things like the sections are going to feel a lot more familiar. So let's start with the plan view or overhead view. We want to get oriented. The first thing that I think stands out is there's a whole lot of dots on this detail. Just like with the column we looked at, a dot means that the bar is coming in and out of the page, or we're looking down on top of it. So that means there's going to be a bunch of vertical bars here. So to satisfy our curiosity on that, we can look at the section cuts. And there are 2 for this footing, cutting it across each major direction. Zooming into section AA, we get to see that what these dots actually are. Turns out they're long vertical ties which wrap around the top bars and the bottom bars. That's a lot of vertical bars. Now, I want you to know that engineers design for each specific bridge. So the details you see here are not necessarily going to be the same details you see on other structures. That's why you need to follow the plans. Instinct can only get you so far. I've seen pile caps with fewer vertical bars than this, and that's okay. It depends on the math that was used to design this. Remember that concrete is garbage in tension, so the engineer's calculations must have shown that for this column, there's a condition where this footing could be damaged without that steel. For example, if an earthquake tries to bend this column over, it would pull up on that side of the footing, causing tension, and that could potentially damage it. The steel's there for a reason. Continuing our curiosity, what does the other section look like? Well, it looks very similar. I know it's kind of small, but can anyone here spot what the difference is between those two details? Yeah, it's kind of small. I'll just move on. There's really only two. The first one, it's a center line, right? It either says center line bent or center line column and footing. And the horizontal bars, they're on the top of the horizontal line on the one, and the dots are on the bottom of the other one. The center line thing is nice. It lets us get a sense for where we're looking without a north arrow. We're looking down the center line of that bent. The other column is going to be directly behind this one. But it's the bars that are really important here. These bars have to be stacked on top of each other somehow. And believe me, which one is on top can actually matter, especially in thinner elements, like bridge decks. This is another one of those times where I want to pause and remind you again why plan reading is so important. And that's why plans have so many pages and details. It's because the engineer has tried to plan out every aspect of this bridge's layout and use that information in the design. So now let's drop section BV and look at that plan again. Aside from all those dots, the next thing I notice here is the fact that the column reinforcing is shown. If you remember the column page, no reinforcing was shown for the pile cap. So why would we show the column reinforcing here? Well, it's because that bottom part of the column is cast into the pile cap. So even though there's going to be another stage of construction to get that column just right, that column needs to be in place now. Pile caps are definitely more complex than columns because there's simply a lot more steel going every which way. At this point, we've taken a high-level look at the plan view and the sections, but nothing we've talked about so far actually gave you enough information to inspect anything. Yes, there are vertical bars. Yes, the column needs to be there. All that stuff will help you get a feel for what this thing will look like, but ultimately it's the call-outs that tell you what needs to be done. Let's look at the actual rebar in this pile cap from bottom to top. The top and bottom mats of horizontal rebar are shown here. How do you know? Because there's a little line that points from the bar to that callout. Sometimes the information provided will be very basic, like 11F1, top and bottom. This tells us they're number 11 bars, 11/8, 1/3 inch diameter bars, and that they're placed on the top and the bottom of the pile cap, but nothing about how many are placed and where. So we need to zoom back out to the plan view where we have more information. Showing this information in one place is done on purpose because bridge design takes months. During that time, the engineer might change something. And if they do, it's really important that they don't have callouts that are wrong left somewhere in the plans. So requirements tend to be shown once, with secondary callouts giving very basic information. So let's look at that detailed callout. This says we have 19 number 11 bars marked F1. Then it says AS, top and bottom. AS stands for as shown. As shown means that the bar, the way it's drawn, is how it should look in the field. I'm glad that I had the opportunity to talk about as shown to you, but usually when you see as shown, it's because the layout is too weird to describe with measurements. For example, here we have an as shown on the bars in a parapet. You can see that they rise up the parapet at equal spaces, but at the top, instead of 2 bars, there's only 1. They also tied with the vertical bars, but because that front face is sloped, it's not a standard width. So rather than trying to describe every bar, the word as shown is used to point out that you just need to pay close attention to the way it's drawn. Anyway, so in the case of this pile cap, it's not quite so challenging as that parapet was. We can see that the spacing of the bars is 8 equal spaces. Then there's a 1 foot 4 inch gap to the next set of 8 equal spaces. This is a thing that confuses a lot of people. First, we counted the bars, 19, but then we started counting the spaces, 8 and 8, and a 1 foot 4 inch gap. That's what, 17? 19 and 17 are different. So what's going on? First is just remembering that bars are on each side of a space. So 3 bars and 2 spaces are describing the same thing. The next thing to think about here is perhaps why the engineer wrote as shown. Because right in the middle of that 1 foot 4 inch gap, there was another bar placed at the center line of this tile cap. It's a lot easier to see in the section cut. So 8 spaces relates to 9 bars. This is on both sides of the pile cap, plus that extra one down the middle. 9 plus 9 plus 1 is 19 bars. So that's all the horizontal bars. But that's also why seeing the total number of bars, seeing that count, very important. And seeing those bundles used, very important, right? If there's an extra bar laying out on the side, like, well, where's that go? Let's dive back into that plan, see if we can figure out what happened. So now let's mark that to show that we thought through this one. And what's this on the side? That's 19, 6F4, AS, EF, bundled with 11F1. That sounds new. Let's talk through that. We have 19 bars, size 6, with a bar mark of F4, placed AS as shown on EF, which stands for, oh man, that didn't fit in the thing, each face. This big old block of pile cap has 4 faces. We usually refer to the vertical side of something as a face. So you'll often hear front face, back face for something like a wall. But here we have 4 faces because this is a big blocky foundation. So we have 19 bars on each of the 4 faces, and they are bundled with the 11F1 bars. Bundled just means that the bars are side by side and tied to each other. So looking more closely at this foundation picture, you can see what it means to have bars side by side and tied to each other, or bundled. This is how the engineer is letting you know that where these bars are. They're tied to the other bars at 11, the 11F1 bars that were already placed. Any questions on that? No? One thing that's fun to notice here, we're talking about tying bars together. Ties, little wire ties, are used to make sure that the bars stay where they're supposed to be. So whenever you have bars crossing each other or next to each other, you will see lots of little ties holding them together. Because we use epoxy coated bars, those ties should be plastic coated, because like we said before, damaging that epoxy is just how we're going to get problems. So having base metal tied real tight to a bar can damage that coating. So you should always see plastic coated ties, almost always. If it's galvanized on galvanized, you might see a galvanized tie wire, but it's much, much more common to see plastic ties. Okay, so let's highlight the 6F4 bars now that we know what those are. So what's next? How about the 49 number 5 bars marked F2 as shown? Typical per quadrant. Okay, quadrant being each of these 4 quarters of the cap. These are the dots that we looked at first. So we've already figured out what they are, but where do they go? They're marked as shown. So we need to pay close attention to the detail. And it looks like they're placed at most of the places where the horizontal bars cross. Most, but not all. So the as shown is going to require you to look at the construction and the drawings and count bars, or highlight the drawing as you check bars and pay attention to the places where there aren't any bars. So like above the piles, looks like that's where they're not shown. That's good. We can mark off the 5F2 bars. Next one I see is the 6F3 bars, or number 6 bars marked F3. Here we see that this is on all 4 faces of the pile cap. It's also interesting to note that the minor callout for the bar is on the plan view, while the more detailed callout is in the section. This is because the spacing information just makes more sense there. And what do we see? 3 6F3 bars at equal spaces on each face. At this point, I think we all know what that means. So let's move on through this. Finally, we can scan through the remaining bars and see that they're all C bars. 6C, oh, did we have a question? 6C3, 6C5, 6C6, 11C1, 11C2. If we hadn't already looked at the column sheet, it would be good to look there now and know what those bars actually are. But we already did. So at this point, I think we have a good understanding of the rebar in the pile cap. Here's another pop quiz, and this one is a bit of a trick question because there's some information missing from these details. Can someone tell me what the clearance or concrete cover is on the top of the pile cap? Anyone willing to risk a trick question? Close. Okay, so we have a 3-inch clear cover to the bottom and 3-inch clear to the side, but there's no information provided here for the distance from the top mat. Now, I said before, it's sort of wherever those appear to make sense when you have a typical, but there's no typical on those. And that top, even if it was a tip, that top is a very different surface from the bottom. So what do we have here? This is one of those memorization things. On the situation and layout page, there were those general notes that I mentioned very briefly. These notes apply to the entire plan set. So they say to use A706 steel in the columns, something that I said in passing before. They also say to chamfer or blunt the exposed concrete corners to 3/4 of an inch unless detailed differently. And they say to provide 2-inch minimum concrete cover to reinforcing steel unless shown otherwise. So anywhere you don't have a different clearance shown, the clearance is 2 inches. That means that the clearance at the top of this pile cap is 2 inches. It also means that you really need to take a moment to search for those clearance numbers because they aren't always shown in every detail. And now that we've talked about general notes way back on the front page, I want to make sure you're all aware of sheet notes. Somewhere on most sheets, there will be a set of notes. Unlike the general notes, which apply to all of the sheets, here we have notes that just apply to the sheet that they're on. Sometimes those notes are very basic, like see the pile details sheet. You notice the quotation marks, meaning that that's the actual title of that sheet. But some notes are very specific and important, like note 4, footing reinforcement may be adjusted slightly up to 3 inches to avoid conflict with column reinforcement. This provides a very specific instruction. So reading the notes is a quick task, but may give you the information that you didn't know that you needed. Like we said before, your bars don't have to be perfectly like on the dot, 8-inch right, got to be right there, but they should be approximately in the right space. And 3 inches is actually quite a big deviation when you're setting your bars at every 6, right? So having a note like that it's important to see. Okay, that's pile caps. Any questions before we move on to decks? I love that picture. I mean, it's so hard to see scale, right? When you're looking at a drawing set, like with stick figures, right? And then you look at a picture of rebar that doesn't have men working inside it. It's like, oh, okay, it's kind of big. But then you see some guys actually placing bar and you're like, oh man, what we do, look, bridges are big, right? And they're really important structures, or as to say at the beginning, they're the best. Bridges are the best. And this is part of it, right? This is massive stuff, very important stuff that we do. Okay. Now let's talk about bridge decks. I have it labeled as hard, but now that we've gone through the columns and the pile cabs, it's really not going to be that hard. But at the same time, bridge decks are critical. The bridge deck is where all of the action happens. So it's where quality construction and therefore quality inspection really pays off, like in dollars, because bridge deck repairs are expensive. Let's take a look at the pictures here. At the bottom of the screen, we see nice brown pothole caused by bars that didn't have enough cover. The bars didn't rust. The epoxy coating is still on them, but they're so shallow that the traffic on the deck vibrated against the bars and it just popped right off. Then you have the big exposed deck on the right. Here, you can see that the bar depth is actually inconsistent, shallow at the parapet, and very deep in the middle. Based on the corrosion we're seeing on the shallow side, we can determine that the lack of cover there led to early corrosion and concrete damage. Once the concrete's damaged, it spreads and even ruins the part of the deck with too much cover. Although having too much cover comes with its own problems. Now, I don't think we had epoxy on those bars because in the old days we didn't. But epoxy isn't perfect, and there are some states, especially on the East Coast, who refuse to use epoxy bars at all because of the failure rate of the epoxy coating. Then on the left, we see an attempt to seal cracks that have worked their way entirely through the deck. Crack sealing is very expensive. Usually this problem is more of a concrete quality issue than a reinforcing steel issue. But the point is that decks are sensitive to problems and constantly battered by traffic and weather. So the better we can make them during construction, the better we are in the long run. Now let's look at some bridge deck reinforcing plans. Because bridge decks can be long, sometimes the plans need to be split onto 2 sheets or more with a match line. Just like with roadway plans, the match line just shows where one sheet stops and the next one starts. But something that's a bit interesting about structures plans are the double arrow dimensions. Double arrow dimensions means that what this line is measuring continues past this page. So on the bottom, we see a measurement of 130 feet for span 2. Span 2 continues on to the next page. So this measurement has a double arrow. The same is true for the reinforcing callouts. This measurement for 252 4S9 bars at 1 foot spacing extends onto the next page. And you don't need to guess how far onto the next page either, because if we flip the page, we see the same measurement with a double arrow going the other way. So you can connect those lines and look at them like it's just one dimension line with 252 bars placed from the start of the dimension on the left side of the first page to the end of the dimension on the right side of the second. Okay, so that's the concept of a 2-page double arrow dimension. But let's dive into content. It can be a bit hard to see with the scale being small, but there are no section cuts on these pages. And that's crazy because section cuts give us those zoomed in details that we need to see to understand what's going on. So why are there no section cuts? Well, that's because we know you need it. So we always just provide a typical section on the next page. Yeah, it's not consistent, so it's a bit confusing. But to read a plan set, you need sections. So if you don't see one right away, try flipping some pages. You might come across it. Okay, so this section from the deck is called a typical section instead of a specific AA or BB, because this is what you should expect to see almost everywhere on the deck. It doesn't matter where that line is cut. This applies typically across the entire length of that bridge. In fact, Now, this typical section is trying to give information about a very specific part of the deck, which is the reinforcing over the bent. So out of curiosity, let's look at those bars. Over the bent means that they will be at the bent. So that's these ones. 64 number 5 bars marked S2 spaced at 9 inches, placed in the top mat at bent 2. I think at this point we have seen this kind of description before, so we know what to expect. And with the typical section, we know that the bars are bundled with the typical bars. But there's also a direct reference to C note 1. The sheet notes always apply to the details on that sheet. So please read them every time. But sometimes the connection is something that the engineer really doesn't want you to miss. So a direct reference is made in the callout. Note 1 says, stagger bars as shown on negative moment reinforcement placement. Detail on deck sections sheet. So the engineer really doesn't want you to miss that detail. And that detail looks like this. This is what it means to stagger a bar. It's a standard term, so you will see it used in other places. Each of these reinforcing bars is the same length, 35 feet on one side of the bent, 25 feet on the other, for a total of 60 feet. But each bar switches. So the first bar is 35 feet to the left of the bent, the second bar is 35 feet to the right of the bent. This is an important engineering requirement because the steel is providing a lot of strength to the structure. If all those bars lined up, then that strength would stop at one spot on the bridge, and we'd probably get a crack there. By staggering the bars, we smooth out a strength transition, which prevents that from happening. The other thing that you should be aware of is the term negative moment. I think you've all experienced this stuff before, but maybe you didn't have the engineering terms for it. In a simple beam, you push down in the middle, it bends down, maybe breaks if it's not strong enough. Because that's what we see most often. We call that downward bending, positive moment. Negative bending is the opposite, a bending up. This happens when you have a support that you're bending over the top of. This is called negative bending. So in this bridge, the reference to a negative bending is letting you know why we need those bars. It's because the force here is opposite to the more common positive bending. Now back to the fun stuff. The next thing I want to point out is not the fact that there's a weird hat pattern at the abutment. That's just actually bars. But the fact that it looks like there are no bars on the deck. Tile cap showing us every single bar. So why is this screen all white? Well, it's because if every bar was drawn in, this sheet would basically look black. So instead, just the bars at the start and the end of each dimension line are drawn in. Everything that's between the start and end is described by the callout. Remember that the callout is what matters. The drawing is just a sketch or a schematic. Unless the callout says that the bar is placed as shown, you rely on that callout. At this point, I feel like I've just been throwing a lot of little facts at you for a while. I don't want to bore you, but before I wrap up on bridge decks, I want to talk through that big call out here, since there's something new there. It says that we have 464 sets of 2 number 6 bars marked as 4 at 6 inches in the top mat. What does that mean? You probably already have it, but it means that there's actually 928 bars here. At each bar location, you should see a set of 2 bars. We know that the bars being called out are the top transverse bars because that's where the callout is pointing to. But to know more about what this means, we need to look at the section. The top transverse bar is called out here as the 6S4 bar. So we know it's the same bar. And looking closely, we can see that there's a second 6S4 bar. So we also know that's the same bar. And looking closely, we can see that there's a second 6S4 callout. And if we look at that detail, there are two bars that overlap at this location. It can feel like it's a bit hard to spot on a cold read, but you know there's a set of two bars. So there has to be a place where it's detailed out. We now know what this is saying, but there's a little problem with the real world not perfectly matching even numbers written on a drawing. When the drawing says 6-inch spacing, what it's actually saying is 6 inches maximum, sort of. If an engineer designs and it needs a bar every 6 inches, what happens if the bridge is a couple inches too long? Well, you add a bar to that smaller space. So in total, the average space is going to be less than 6 inches. And that means you have at least enough steel in the concrete. But how do you handle that out in the field? I'd love it if someone could tell me what they think, how you'd handle that in the field. How would you check 6-inch maximum spacing? Sure, yeah, you go out and measure it, but there's a lot of bars on that. So when you're trying to measure what you want to do, like spot check, absolutely. But it's good to figure out how many bars would be in a 10-foot length of the bridge. Measure out 10 feet, count the numbers in between, and if you have that many bars per 10 feet and they look pretty even, you're going to have enough steel. So when you get to the end of the bridge, you have that one extra bar that was thrown in. They could have put that earlier on in the bridge deck. They might have just smacked it at the end. You might have an extra bar at the end, but you want to have at least the number of bars that you would expect in that 10-foot section. The key is making sure that we have at least enough steel in the concrete. That's a certain number of bars in the right spot, but it's not mathematical precision. Remember that every bar in the marked bar bundles should be used. Okay, back to this. We looked at the top of the callout, so let's look at the other part of the callout, below the line. Here we have 232 number 4 bars marked S5 at 1 foot maximum spacing in the top mat at the overhang. Bundle the bars with the 6S4 bars that we just talked about. And this bar and spacing applies to each side of the bridge. As usual, I said a lot of words. This is a real great summary of like everything we talked about today. And it's all smooshed together in this one shorthand that you see on the plans. But you can read it. I also think that based on that read, you know what bar we're talking about and where it should be on the bridge, even without the section here that shows it. But always remember there should be a section that shows it. If I had another half hour and we had a free supply of Red Bull, we could do what we did on the pile cap and start highlighting each of the bars on this page, but I don't, and we don't, and I don't want to. So you have the tools. You have the tools to read a plan set. And there's just a couple of big takeaways to remind you of and a couple of final comments to make, and then I'll be done. Structures have a language that's pretty unique. We have a whole bunch of names for different parts of the bridge, including different possible options for each of those parts, like steel girder, precast girders. We also have unique words that we don't hear very often that apply to structures and structures plans. But what that means is that structures plans have structure. Once you get used to a structures plan, you'll be 90% there when you look at your next one. There's an established method to how they're set up. You have the situation and layout sheets at the front, reinforcing steel schedules at the back, details and sections of all the critical information in between. Just, so many details. But they're all there to help you understand a singular, very complicated thing. Just zooming in more and more to give you the details that you need. But since they're all of the same thing, the engineer usually only provides one full rebar callout. So you will need to flip between a couple of details to make sure you have the callout that has the information that you need. The full rebar callouts will only be shown in that one spot. The other spots will have minor callouts that are just there to let you know that you're looking at the same bar. So as annoying as it is to have all those sheets in the truck and occasionally flip back and forth to find the information you need, it's kind of the best we can do. Please remember that that information is in there, and the bar marks and reinforcing schedule is your friend. Also remember that reinforcing steel is vitally important because concrete is garbage in tension. So having that bar in the right amount in the right place is necessary. And because concrete can't take tension, rebar has to be coated and covered to make sure that it doesn't rust, because rust expands, pushing on the concrete from the inside and cracks it. Finally, the contractor definitely knows how to build stuff, but the contractor has never built the bridge you're on before. It's the engineer who spent the last year checking every inch and every bar of that structure, then signed it to take responsibility for it, which means the engineer will definitely be sued if something goes wrong. You are there to help make sure that construction isn't the problem. So as I come up to the end of my time, I really want to throw a quick mention on the importance of the specifications. We've talked about it briefly in sort of little one-off things, but this is a plan reading presentation, and specifications are just as important, and they work as a unit with the plans to build the contract requirements. Plans show the final structure, but specifications show the work requirements. When it comes to reinforcing steel, specification 3211 gives you lots of information. Please read the specifications, and they aren't easy either. So if you have questions, please ask someone, ask a mentor, ask the RE, ask the structures group, ask the engineer of record. We all want the job to go smoothly, and questions, that means you're paying attention, and that's great. So that's it. Do we have any other questions? You might find that there is an extra bar. Like if you're doing your 10-foot section and you're counting, it's like, oh, I expected to find 20 bars here and I see 21. That can be okay. Just make sure, try to think about why. If it looks really even, it's probably fine. But if you go down to the end and you're like, well, I expected to see 20 bars here and I only see 19. You know what? They probably put it in the wrong spot and your spacing might be too high. So it is okay to have a little extra, but anything else? Anything you're just curious about in structures? Okay, well, I'm going to be here through lunchtime, so if you ever want to catch me and talk to me in person, you can. Otherwise, I have I think it's printed out, right? You have all the printouts. So my email address, jcorning@utah.gov. So feel free to shoot me an email anytime. Thank you very much.